We're ready to start talking about reactions of organic molecules, and the first group of compounds that we're going to be talking about are the alkenes. Alkenes represent a functional group. Every functional group has a characteristic set of reactions that it will undergo or participate in, and the very characteristic reactions for alkenes is called electrophilic addition. We've talked in general about addition reactions, and you may recall that we said that in order for an addition reaction to take place, you must have a site of unsaturation, and as you know, within alkenes, you definitely have a site of unsaturation. Just to remind you, a double bond is made up really of two bonds, a sigma bond and a pi bond. So right here is our sigma bond. The carbons of alkenes are sp2 hybridized, and each carbon has an unhybridized p orbital. So the second bond of our double bond is made up of the overlap of these unhybridized p orbitals. And what we really have is a cloud of electron density above the plane that's defined by the atoms of the double bond, and below the plane. So it looks something like this. So we have a lot of electron density in between those two atoms when you have a double bond between two atoms, a lot more electron density than you would have between two atoms that are linked through a single bond. If we go back and we consider our friend trans-2-butene and think about the electron density, this figure here in the bottom right shows us an electron density map, and we're going from high electron density, those regions in red, to low electron density, the regions in blue. So you can see that in between those two carbons that make up the double bond, we have a region of very high electron density. Now if we have trans-2-butene floating around in solution, and an electrophile comes and floats by, well, that electrophile, remember, is electron deficient and is looking for a pair of electrons to complete its octet because it is electron deficient. Our electrophile is floating around in solution and gets a look at this region of high electron density and says, wow, I want some of that. What are some electrophiles that we can think about? Well, an electrophile, remember, is a molecule that contains atoms with empty orbitals. It can accommodate electrons. So an electrophile is looking for electrons. These can be positively charged, although they're not always positively charged, but they are always electron deficient. And here are a few examples of typical electrophiles. That a proton is also an Arrhenius acid. It's a Bronsted-Lowry acid. We also consider that a Lewis acid. It's electron deficient. There's a couple of other electrophiles here that you may not have thought about before, and if we look at this carbon has a positive charge. It only has 6 electrons in its valence shell. That means that it is electron deficient, and it is also a Lewis acid. In the molecule BF3, boron has only 6 valence electrons. It is neutral, but it is also electron deficient because it does not have an octet. So BF3 is also a Lewis acid. So our electrophilic addition reaction can really be boiled down to acid-base reactions in the Lewis sense. So the first reaction that I talked to you about in our previous video was an addition reaction that I'm showing you right here. This is the addition of HBr to an alkene, to trans-2-butene. This particular example is an example of an electrophilic addition. I think you can see why it's an addition reaction. It's electrophilic because our substrate, our trans-2-butene, is being attacked by an electrophile. So let's go and have a look at the mechanism for this reaction, or in other words, the step-by-step process of bond breaking and bond making. So here's our reaction, and throughout this course you're going to be presented with reactions, and I'm not always going to show you what the product is. You're going to have to figure out on your own what the product is. So let me just give you a few hints about how to proceed. So for instance, I might give you a reaction starting with a molecule that has 2 different functional groups. And depending on what the reagents are, you're going to have to figure out where that reaction is taking place, which functional group. Let's think about what you should be considering. First, you want to look at the nature of each reagent or each reactant. And here we have the organic substrate. You can see that this functional group is an alkene, and you have to think about what kinds of reactions alkenes undergo. And for our purposes, the only reactions that alkenes undergo that we will talk about in this class are electrophilic additions. In order for this reaction to take place, you have to have an electrophile. What is the nature of this reagent? This is an acid. It's an Arrhenius acid, a Bronsted-Lowry acid, and it is a Lewis acid. Another important factor that you're going to think about sometimes is the solvent that the reaction is taking place in. And often we put the solvent directly under the reaction arrow. In this case, this reaction is taking place in water. So let's think about what happens when we put HBr into water. Remember that HBr is a strong acid, and when I put HBr in water, I have an acid-base reaction with water acting like the base and accepting a proton. I can show you this reaction in a slightly different way. Now I'm going to use the curved arrow formalism to show you the path of electron movement. Now recall that the HBr bond is a polar bond, so we have a partial positive charge on the hydrogen and a partial negative charge on the bromine. Oxygen of my water molecule is going to act like a base, and it's going to abstract that proton. Remember that I'm using the curved arrow to show the flow of electrons, or the movement of electrons, starting from electron-rich and going towards electron-poor, going from a lone pair to a partially positively charged proton. This pair of electrons that's shared between the hydrogen and the bromine is going to be given to the bromine. So I'm going to end up with H3O, or hydronium ion, and Br-. H3O is going to act as my electrophile in this reaction. Very often I'm just going to abbreviate that as H+, but you should remember that H+ doesn't really exist in water. It actually exists as H3O, or hydronium ion. What happens between our hydronium ion and our alkene? Remember that H+, it really exists as our hydronium ion. I'm just abbreviating this as H+. H+ is an electrophile. It's a Lewis acid. So it's floating around, it gets a look at that region of high electron density, and it's very attracted to it. H+ is going to grab that pair of electrons that makes up that pi bond, and I'm going to end up with a new intermediate. And there it is. I've formed a bond between this carbon and hydrogen, and now this carbon is electron deficient. This new intermediate that I formed is called a carbocation. So this is an electron deficient carbon. Don't forget that I also have Br- floating around in solution. My carbocation is now an electrophile, and my Br- is a nucleophile. The simplest thing that can happen here is my Br-, my nucleophile, donates a pair of electrons to the electrophile, and this neutralizes the charges for each of them. So let's give a pair of electrons from Br- to our carbon. And now I've generated my final product. You may remember our reaction coordinate, or our reaction profile, from an earlier video, and if I were to place my starting material and my product on my reaction profile, I could place them at the beginning and the end of the reaction. At the intermediate stage, I would place that carbocation. So a carbocation is a reaction intermediate, and remember that is a species that exists in a potential energy well. It has a finite lifetime, so it is something that we can actually observe, and we know it really does exist. An electrophilic addition reaction mechanism is a two-step mechanism with a carbocation as a reaction intermediate. I want to talk about one final but very important consideration with respect to electrophilic addition to alkenes, and that is the issue of regioselectivity, or in other words, which carbon is going to get the electrophile and which carbon is going to get the nucleophile. In the addition of HBr to trans 2-butane, it didn't matter which carbon our proton initially added to. I could add to this carbon or I could add to that carbon, and I'm going to generate the same product. First I could add bromine, and I'm going to put the HBr in red. I generate 2-bromobutane. If I added bromine to this carbon, this is also 2-bromobutane. So it didn't matter which carbon initially was attacked by H+. That's not always going to be the case, and let's look at a specific example. Here we have 1-butene, and I can add HBr to 1-butene in 2 different ways. Or I can generate, in other words, 2 different regioisomers. In my first regioisomer, I add bromine to carbon 1. In my second regioisomer, I add bromine to carbon 2. And I'll just put the hydrogens on. I can generate 1-bromobutane and 2-bromobutane. Well, let's have a look at the intermediates for each of these reactions. My first intermediate, I'm going to add hydrogen to carbon 1. And that puts the carbocation, or the positive charge, on carbon 2. In my second reaction, I'm going to add hydrogen to carbon 2, and that puts the carbocation at carbon 1. For each of these, remember, we can have our second step. We have the reaction between our carbocation and Br-. So I will generate from this 2 different products. Here we have 2-bromobutane, and our second product would be 1-bromobutane. Well, it turns out that our major product is 2-bromobutane. And the reason for that is our secondary carbocation is considerably more stable than the primary carbocation. This is an important consideration which does affect the outcome of the reaction, or in other words, it affects which regioisomer is generated. This brings us to an important rule in organic chemistry called Markovnikov's rule. You also may hear this pronounced Markovnikov. You also may see this spelled differently. Markovnikov's rule is named after a famous Russian chemist. Markovnikov's rule is used for predicting the major product of an electrophilic addition when you're adding to an unsymmetrical alkene. I've highlighted here major, and often in organic reactions you can generate more than one product, and it's important that you're able to predict what the major product is going to be. I've also highlighted the word unsymmetrical. You recall that when we were adding to trans-2-butene, it didn't matter which carbon the proton added to initially. Because the alkene is symmetrical, either way gives us the same product. When you have an unsymmetrical alkene, or in other words, the groups that are attached at opposite ends of the double bond are different, you will always have the potential to generate 2 different products. So this really comes about as a result of the relative stabilities of the carbocation intermediates. A tertiary carbocation, or a carbocation in which the carbon that bears the positive charge is attached to 3 different groups, is the most stable carbocation. This is followed by secondary, primary, and the methyl carbocation. So the more alkyl groups, or the more R groups that are attached to the carbocation, the more stable the carbocation will be, the more of that carbocation will be generated, and that will lead to your major product. So if I were to add HBr to this unsymmetrical alkene, 2-methylbutene, I could generate 2 different products that arise from the 2 different carbocation intermediates. In these products I'm showing both with and without the hydrogens just for the sake of clarity, and it turns out that our major product arises from the tertiary carbocation. So when I say the halves get more, what I mean is the carbons that have the protons already are the carbons that are going to get more protons. So now it's your turn to try to predict the product. Go ahead and put the video on hold and see if you can predict the major product from the electrophilic addition of HCl to these alkenes. If these are the products that you predicted right.